In this final video for circular motion, let's take on some circular motion scenarios that have three or more forces that all combine to give you a net force towards the center, creating that circular motion. So let's start by just reminding ourselves of the different forces that are acting, and basically here acceleration in a circle, force in a circle versus linear velocity, angular velocity, radius, and period. Now, there is an old school fair ride that you can see still traveling around in county fairs. It's called the Rotor or the Starship 3000 or something like that. Basically, it's a ride where you go into this giant barrel with walls that the whole barrel starts spinning. And as you spin, you find yourself getting stuck to the wall. Some versions, like this old school one, the floor actually drops out. Some versions, the wall is slightly sloped and there's like a track that you're on a bed that slides up. In both of those versions, you lose contact with the ground and your entire weight is being supported, sticking to the wall. So we need to know the forces that are at play here. There is a force of gravity, but more importantly, there is a normal force that is the surface of the wall that is pushing perpendicular to the wall, that's pushing towards the center. Now the force of gravity is pointing down. Fg is mass times gravity. And then here, there must be a force pointing up to support that force of gravity. Turns out that that is the friction between you and the wall, Ff. And as a reminder, we haven't seen this in a while. Ff is equal to mu, the coefficient of friction, times the normal force. So let's draw this here. This is going to be a really useful kind of starting point for us. Here, this is just a cross section. We're looking at it from the side. The normal force is pointing towards the center. Force of gravity is down. The force of friction is up. So why don't they fall down? Well, it's all to do with this friction. If that wall was coated in butter, it wouldn't matter how fast it was moving. You would never stick to the wall. It would never be able to support your weight because the mu would be too low. It wouldn't matter how big the force, normal force is. But typically, you can spin fast enough that you can get enough friction to support the weight. So you can't forget about this friction. We can basically use this equation help us understand what's happening. Normal force is Fn, coefficient of friction is mu. That's just a measure of how sticky or slippery the surface is. And the bigger the normal force, the bigger the friction. Bigger mu, the bigger the friction. I also know that if this object is moving in a circle, the object being a person, uh, it's equal to mass times acceleration. And I know from this picture that the force of gravity and the force of friction have to cancel each other out. There is no upward or downward acceleration that's happening. So those two things cancel each other out, and you're left with the only force being the normal force. So we're going to say that the overall force, because the other two canceled, is just equal to the force of normal force. It's the surface pushing. So that means if you know the net force, you can find the normal force. If you know the normal force, you might be able to find the force of friction. If you know the force of friction, you might be able to find the force of gravity. And all of this is going to be factoring in with our circular motion and the acceleration of an object that's moving in a circle. So let's see it with numbers because I think it'll make a little bit more sense. This rotor ride is one where it presses you against the walls with a spinning rotor as the floor drops away. The coefficient of static friction between the wall and the 75-kilogram rider is mu equal to 0.06. If the ride is rotating at an angular velocity of 5.2 radians per second, what must be the radius of the rotor? All right, so we're have to figure out what the radius is eventually. Let's first start by listing what we know for sure. We know that FF and Fg are equal and opposite. This person is not accelerating up, not accelerating down. Those forces should cancel each other out, which means we know what those are going to be. Mu times Fn is the force of friction. Mass times gravity is the force of gravity. And I can plug those in to figure out what the normal force is going to be. Normal force in this case is 12,250 newtons. Again, I know certain things are related to each other. The only thing I didn't know was the normal force. So normal reaction force is equal to the centripetal force, or in other words, just the net force causing that circle. So if I know that the net force is mass times acceleration, and I know a variety of different ways to calculate acceleration, one using v, one using omega. In this case, angular velocity is omega. I'm going to use the omega version and basically say the net force, this is the same as the normal force because it's the only force that doesn't cancel, is equal to mass times the angular velocity squared times the radius. I plug in the things that I know. The normal force I had already calculated. The mass is given. The angular velocity is given. The only thing I don't know is r. And I can solve that r, the radius of this ride, is 6 meters, which kind of makes sense. It's about 18 meters. It's a pretty big ride overall. But that's what's required for the rider to be supported with this coefficient of friction. Now, if that coefficient changed or the speed changed, that might change, but this is kind of the worst case scenario given these examples. Now, we did all of that by plugging in numbers. Turns out that you don't actually need the mass. I want to show you why that's the case. It doesn't matter how heavy the rider is, they will all get stuck to the wall at the same time, presuming that they're not wearing different types of clothes that would cause a different change in coefficient. So if we know that FF is equal to FG, and as we saw before, FF is mu times Fn and FG is mass times gravity, and we plug that in. We also know that the net force is mass times acceleration, and the net force is equal to the normal force. That means I can actually take this and substitute in instead of normal force my equation for net force, mass times acceleration, using acceleration as omega squared r, and I get this. Instead of mu times Fn, it's mu times mass times acceleration, which is mass times omega squared r. That stays equal to the force of gravity, m times g. And you'll notice that mass shows up on both sides. So regardless of what it is, if it's 75 kilograms or 75,000 kilograms, mass cancels, and you're left with just mu times omega r, or omega squared r is equal to g. You can rearrange this to solve for r, and you would get exactly the same number. We know what mu is, we know what omega is, and we know what g is. Um, that is a nice strategy that you can use if you don't know the mass. All right, so to assemble this along with our other examples that we'll see later on, if we have an object or a person in a rotor, we know that there is a force of gravity going down and a force of friction supporting them going up. Those are equal to each other. If this object is spinning around in a rotor and stuck to the wall, there is also a force pointing towards the center. In this case, it is the surface of the wall pushing inward. That is the normal force. If FF and FG cancel each other out, that means that my overall net force is entirely coming from Fn. So that is a hidden equality there as well. So in this scenario, these two are going to be kind of your magic equalities that allow you to unlock different parts of your circular motion scenario. All right, let's look at scenario number 2, an object going around a curve. What is providing the centripetal force causing the car to move around a curve? So here's our car coming around the curve. Let's talk about what forces are happening. There's a velocity that's certainly happening, but that's not necessarily a force. I think the easiest way to see this is to look at the car kind of from the perspective of right behind it. We know that there's a force of gravity going down, that's mass times gravity. We know that there's a surface here and a surface can push. So it's being supported by Fn. And in this case, just like before, these vertical forces cancel each other out. Fn and Fg are going to be set equal to each other because the car is not accelerating upward or downward. It's only accelerating in this circular plane. Now, there must be a force going towards the center of the circle. Turns out that it's friction. If the road was too slippery, there's no amount of forces or weight that would change that. You would slide off that road, which is what you'll see if it's icy. So this inward force, FF, is equal to mu times Fn. And again, we'll see some interplay with that. Fn and Fn are going to be related to each other, so we're going to see how all that connects together. But again, if these two cancel, my overall net force is going to be entirely from what's left. Fn and Fg cancel, so we have FF equal to the net force. All right, let's see this with some numbers. A car of mass 1240 kilograms moves around a bend of radius 63 meters on a horizontal road at a speed of 18 meters per second. If the car was to be driven any faster, there would not be enough friction and begin to skid. What is the coefficient of friction between the road and the tires. All right, let's draw our free body diagram, draw the forces that are acting. We know that the mass is 1240. We know that the radius is 63. We know that the velocity is 18 meters per second. On my drawing, I know there's a downward force. That's the force of gravity, mass times gravity. I know there's an upward force of the surface supporting. That's Fn. And I know that there's a sideways force causing it to move around the curve. That's Ff, which is mu times Fn. Now, in order to solve this problem, I need to think about what equalities kind of exist within that picture. I know that Fn and Fg have to equal each other. They have to cancel each other out. I know enough here, because I know the mass and gravity, to find what Fg is, which means I know what Fn is. So Fg and Fn are both going to be equal to 12,152 newtons. Now, those are going to be the same, which means that all of the remaining force comes from Ff. So the net force is equal to Ff. And my net force is just mass times acceleration. In this case, I'll say mass times v squared over r because I know a velocity, not an angular velocity. That's equal to the net or the friction force, which is mu times Fn. I know what Fn is now because I solved that here. I know what the velocity is. I know what r is. I know what the mass is. I don't know what mu is. So I can solve this for mu and find that mu is 0.52, uh, and that is a frictionless number. That is telling me the coefficient of friction required uh, between the road and the tires, otherwise we begin to skid. Now, it could certainly be more than that, but if it was any less than that, we would start to see skidding if this is the motion that's happening. Now, just to be clear, this could also be solved without mass because Fn incorporated the mass to begin with, so that mass cancels out. You could do the same sort of math skills that we did with the rotor problem to do this without the mass. All right, if you were to take this curve, not perfectly at a horizontal road, but instead bank the road a little bit, it will actually allow you to go a little bit faster. That's why curves are banked for any racetracks. They have a slope to them. The reason for that is we know that there needs to be some inward force of friction. That's what was creating this inward force. But if you have a banked curve, your normal force is no longer straight up. Part of it is up, but part of it is pointing in towards the center, which means not all of the force towards the center has to be from friction. That you can actually travel faster because you have more center facing force due to that components of your normal force. All right, so altogether, as we saw before, we have a scenario where you have a force up and a force down that cancel each other out. So in this case, instead of FF supporting FG, we have FN supporting FG. And then, as we saw before, there is an inward facing force. In this case, it is FF to provide that net force causing the circular motion to happen. Very similar to how FN did it on the rotor. All right, we have one more scenario. This is a scenario where you have a circular pendulum. Basically, you have something moving on a circle that's moving around in this conical shape. Now, when this happens, there are a few different forces that are at play that will allow us to understand the circle and how everything cancels out. So let's look at this as a picture. We've got a ball on a string. There's two main forces. We have a force of tension, which can only pull in the direction of the rope. And then we have a force of gravity that's just going straight down. Now, this here uh, are the only two forces, and that I feel weird because our other examples had three forces. Well, it might actually be helpful for us to think of this as three forces instead of two forces, because while this is moving up at an angle, part of it's pulling up and part of it's pulling sideways. So we can think if the overall force is in towards the center, that's the only acceleration that's taking place, is not moving up or down. That means that the vertical forces must cancel. So we can basically split that up into a y and an x component, and it's the y force that cancels out Fg, and it's the x force that cancels out the net force. So here, my net force is entirely the horizontal direction of my tension, and the force of gravity is entirely supported by the vertical component of my tension. All right, let's see it with some numbers. What is the net force required to cause a 0.12 kilogram mass to swing in a horizontal circle with a string at an angle of 30 degrees? All right, let's see how this all plays in. We've got Fg going down. I'm just going to split up into components right away and say Ty going x, or Ty going up, Tx going towards the center, and my overall net force is going to be pointed towards the center of the circle. I know that F net is equal to Tx, so that's kind of my target here. I'm trying to find the net force, which means if I can figure out what Tx is, I have found it. So let's figure out what we know. We know that there is a triangle here that exists, that this 30 degrees is happening up here. That 30 degrees is representing the difference here in the triangle, Ty, Tx, and T is the tension, which means that the tangent of my angle is equal to the opposite over the hypotenuse. So I can relate Tx and Ty through the tangent of theta, which means I can calculate Tx if I know what Ty is and I know what the angle is. Now, Ty is just equal to the force of gravity because there is no acceleration in the vertical direction. Those have to cancel each other out. And I can find what the force of gravity is. That's mass times gravity, 0.12 times 9.8, which is 1.18 newtons. If I plug that in for my Ty, I've got 1.18 newtons times the tangent of 30. That gives me 0.68 newtons, which if net force is equal to Tx, my net force is also 0.68 newtons. Now, I could probably take that further. I know some stuff about this that I could solve for some of the motion, the acceleration, all of those things. But for now, we're just going to leave it as a net force because that's what it's asked for. Be careful. One of the biggest slip ups that you can make on this type of problem is there are actually two triangles. They are similar triangles that use the same angle, but there is a triangle of lengths and distances. So the length of the string, the radius of your circle, and how far you are from the ceiling or the top. And there's a triangle of forces. This is the tension force Ty, Tx. In that last problem, we were only dealing with this triangle of forces. But say you have a situation where you know what the length of the rope is and you know the angle, you might need to use that length of rope and angle to calculate what r is, because r is a really useful number in circular motion and it's in most of our equations. So you might be able to use that length and distance triangle and the force triangle, but keep them separate. They should all have units of meters or centimeters, or all have units of newtons, but they should never mix. All right, so seeing all of these in the same place, each one of these had a situation where the vertical forces canceled because we had no overall force moving up or down. In this last one, it was the tension in the y direction canceling out the force of gravity. And in each one of these, there was an inward facing force. And that inward facing force is the force that remains after everything cancels. So that is the net force causing the circle to happen. That's equal to the x component of your tension. All right, there are a lot of different things, but really these kind of factored into those three main scenarios. You should be able to draw a free body diagram and solve a problem when circular motion is produced by a normal force. So think the rotor problem. Draw a free body diagram and solve a problem when it's produced by a friction force, and then when it's produced by the components of an angled tension force. So think your situation with a rotor, situation with going around a curve with friction, and situation looking at an angled tension force creating that circle.